Hi. In this video entitled Physics Fundamentals of 3D Rendering, we are going to review the optics fundamentals that are essential in simulating the light transfer in virtual worlds. In order to compute the image, the power arriving at the eye from the solid angle of the pixel needs to be determined on different wavelengths. So we establish a virtual world model in the computer memory where the user is represented by a single eye position and the display by a window rectangle. Then we compute the power going through the pixel toward the eye on different wavelengths, which results in a power spectrum. If we can get the display to emit the same photons, that is the same number and the same frequency photons as the real surface would emit, which is visible in the solid angle of the pixel, then the illusion of watching the virtual world can be created. Note that the human eye is sensitive only to the number and the frequency of photons, but is not sensitive to the source of the photons. Thus, we would not be able to distinguish the real world from the virtual one shown on the computer screen. As the human eye can be cheated with red, green and blue colors, it is enough if the display emits light on these wavelengths. The last step of rendering is the conversion of the calculated spectrum to displayable red, green and blue intensities. This step is called color matching or tone mapping. If we compute the light transfer only on these wavelengths, then this step can be omitted and the resulting spectrum can be used directly to control the monitor. One crucial question will be what physical quantity should be computed for the surfaces. That describes the strength of light intensity, and when the pixel is controlled accordingly, provides the same color perception as the real surface here. Note that the pixel is at a different distance and of a different orientation. The total emitted power would definitely not be very good, since it would mean less number of photons for the eye for farther surfaces. Light is an electromagnetic wave. Color is just an illusion created by the human eye and the brain. As the eye is a poor spectrometer, we can cheat it with different spectrum, and the eye finally cannot tell the difference. This fact is exploited by displays, which can emit light just around the 3 wavelengths. So the task is to convert the computed spectrum to the intensities of the 3 lamps associated with the pixel. To solve this, we should understand how the illusion of the color is created in the brain. As the illusion is deep in our brain, we can use only subjective comparative experiments to find out what color really means. In our experiment, we have 2 white sheets. The first one is illuminated by a unit radiance monochromatic light of wavelength lambda. The other is by 3 lamps of controllable intensities and of wavelengths, say 444, 526 and 645 nanometers, which could be seen as red, green and blue. I have to emphasize that we could choose other reference wavelengths as well. They just have to be far enough. This particular selection here is justified by the fact that there exist materials that emit light on these wavelengths, so such lamps can really be created. So in our experiment, a human observer sits in front of these 2 sheets, and his task is to control the intensity of the red, green and blue lamps in order to eliminate any perceived difference between the 2 sheets. If it happens, the monochromatic light and the controlled 3-component light provide the same color and are therefore called metamers. If the same experiment is repeated in many different wavelengths, the 3 color matching functions can be obtained, which are going to be our model of the human perception. Note that the red and some extent also the green function have negative parts as well, which means that, for example, at 500 nanometers, the monochromatic light can only be matched if some red is added to it. So negative light here means that a light that is added to the other side of this matching experiment. In the second experiment, we can try to match 2, 3, and so on component light beams and beams of non-unit intensity. We will come to the conclusion that the corresponding RGB values of polychromatic light are the sums of the RGB primaries of monochromatic components, and also that if intensity of the beam is not unit, then the RGB intensity should also be multiplied by the same factor. So this means that color perception is a kind of linear system. Based on these experiments, we can establish the Grassmann laws of color science. It says that any spectrum can be matched with 3 primaries by weighting the monochromatic components by the color matching functions and adding up, which means integration if all possible wavelengths are considered. So a physically plausible simulation would be executed on many different wavelengths, and the result is also a spectrum. The final step of rendering is the conversion of the computed spectrum to RGB values that can be displayed by the computer monitor. However, in many cases we use just an approximation. We assume that light sources emit light directly on the wavelengths of red, green and blue. Thus, we can immediately get the RGB values without any integration or color matching. Note that in this rendering process, the process itself is non-linear, so it is only an approximation. Non-linearity comes from the fact that light source intensities and material reflection parameters are multiplied together in order to get the reflected intensities. So this RGB model, although very simple, it is not perfect, it's only an approximation. If we want some efficient computation scheme, we should work with power density instead of the power. This is computed with respect to the solid angle in which the light is emitted and with respect to the size of the projected or visible surface. The density computed as the power divided by the projected area and the solid angle of emission is called the radiance. So this formula should be interpreted in the following way. We consider a small surface area, delta A, and a small solid angle, delta omega, of radiation. This small surface area radiates delta phi power into this small solid angle. If we take the radiated power and divide with the visible area, the visible area also takes into account that when we look at the surface from a non-perpendicular direction, it looks smaller, and the factor is just this geometric term. And we should also divide the power with the solid angle of the radiation, delta omega. Experience and important theorem state that if two surfaces have the same radiance, then they look identical no matter whether they are at a different distance or have a different orientation. And this is exactly what we need when we want to replace the illusion of a surface at an arbitrary distance and of an arbitrary orientation with a pixel of the computer screen. The proof of this theorem is based on the fact that if in a solid angle the eye gathers the same number and frequency of photons, then the eye would not be able to distinguish the source of the surface. So let us compute this power for two surfaces that are seen in the same solid angle and have the same radiance. The formula of the transferred power can be obtained from the definition of the radiance, multiplying both sides by the denominator. So if the surface is closer, then its area is smaller, but the solid angle in which the pupil can be seen from here is larger. Both this green solid angle and the area change when we move the radiating surface farther. But if the surface is farther away, its area increases proportionally with the square of the distance, while the solid angle of radiation decreases proportionally. So these two phenomena are cancelling out. If the surface is seen not at a perpendicular direction, the radiating surface again gets larger, but due to this cosine term in the formula, this is also compensated. So the conclusion is that we should compute the radiance of a surface and set the pixel of the display to have the same radiance. Then the two surfaces will be identical for the human eye. The fact that surfaces having the same radiance but at different distances look similar can also be interpreted as that the radiance doesn't change along a ray. An important remark is that this independence of the distance holds only if the surface is large, or in other words, when we get farther, we can see a larger part of the same surface. Point-like phenomena, like small light bulbs or very distant stars, obviously do not fall into this category. For point-like objects, the radiance is inversely proportional to the square of the distance, as expected. If we have, for example, red monochromatic light source in our room, then only this red color can show up in the room with different intensities, including zero intensity, which corresponds to black. We would never experience, say, green or yellow colors in this situation. Monochromatic light intensity may be modified, but its frequency remains the same. During the simulation of light transfer, different wavelengths can be handled independently, which simplifies the computation considerably. But what is the physical explanation of this phenomenon? In computer graphics, we consider photons in the visible wavelength range, roughly from 300 to 700 nanometer wavelengths. Photon has zero rest mass, otherwise it would not be able to fly with the speed of light. However, it has non-zero energy and impulse, linear momentum. The energy is proportional to the frequency f in this formula, as stated by the famous law proposed by Einstein, and it is also called the photoelectric effect. Einstein got his Nobel Prize for this recognition and not for the theory of relativity. Using the equivalence of the energy and between mass, that is the famous E equals mc squared formula, which is also published by Einstein as a short paper, we can assign a relativistic mass to the photon as the Planck constant multiplied by the frequency and divided by the square of the speed of light. If f is relatively small, then this relativistic mass is small. So when photons meet material, photons collide or scatter by the electrons, or less probably with the core of the atoms. For photons belonging to the visible spectrum, the relativistic mass of the photon is much smaller than the mass of the electron. Thus, the photon bounces off the electron like a ball would bounce off from a rigid ball, or a billiard ball would bounce off from the edge of the table. So an elastic collision intuitively would look like this. So if the collision is elastic, then the photon energy is preserved, and consequently the frequency of the photon cannot change. If the collision is inelastic, then the photon may get absorbed. So this is the photoelectric effect. And as a result, the number of photons can get smaller. The probability of inelastic scattering also called the albedo, associated with a collision is energy dependent. So summarizing, when photons meet electrons, their number may get smaller, but their energy level and consequently their frequency remain the same. So this is the reason that in computer graphics, wavelengths or frequencies can be handled independently. The simplest arrangement for the light and object interaction is a single plane separating the space into two half spaces. In one half space we have the air, and in other half space some material. Suppose that a light ray arrives at the plane from the air. According to the laws of geometric optics, the illumination is broken down to two components, to a reflected component that meets the law of geometric optics, and to a refraction component that meets the refraction law, or also called the Snell's law, stating that the ratios of the sines of the incident and refraction angles is equal to n, the index of refraction of this material, which represents the ratio of speeds of light here and inside the material. The Fresnel equations also tell us the amount of reflected light, and this fraction is usually denoted by F. Because of energy preservation, the incident light times 1 minus the Fresnel component goes into the material. Here we propose a simplified form of the otherwise rather complicated Fresnel equation, but it is going to be sufficient for our purposes. In this formula, F0 expresses the reflection probability of the photon when it arrives from a perpendicular direction. F0 is a function of the index of refraction n and the extinction parameter kappa. Let us take glass as an example. The extinction coefficient of glass is negligible because it's usually negligible in all non-metal materials. In metals, the kappa extinction coefficient is really significant. The index of refraction of glass is 1.5. Thus, substituting these parameters into this formula, we can see that F0 is 4%. So indeed, when we look at a glass window perpendicularly, the image is determined by your own reflection only with 4%, while the outside view determines it with 96%. However, when the direction is not perpendicular, F gets larger because of this term, and glass becomes mirror at grazing angles. The Fresnel function depends on the wavelengths and also on the incident angle. When we see an object, we can observe surfaces of many different orientations, so we perceive the Fresnel function as a whole. This is why we can distinguish gold from copper, although both of them are yellow. To render smooth surfaces, we should compute the ideal reflection direction. Assume that incident direction v and surface normal n are unit length vectors. This assumption simplifies the formulae quite considerably. So incident v is decomposed to a component parallel with the normal vector and another component which is in the same plane as the other two vectors, which is perpendicular to it. The length of the parallel component is the projection of v onto n, which can be obtained with the dot product. The perpendicular component, that is here, is obtained by requiring the sum of the parallel and perpendicular components to be equal to v. Then the reflection direction r is expressed from these two components. So we can establish this formula for the reflection direction. For the amount of reflected light, we use the approximation of the Fresnel function. For computer simulation, we need two functions. Function reflect is the implementation of the reflection direction formula. Function Fresnel determines the portion of light being reflected. As the index of refraction and the extinction parameters depend on the wavelengths, the result is also a spectrum. So that's why we use VEC3 as a return parameter, because it can be different on the wavelengths of red, green and blue. The refraction calculation is similar, although a little bit more complicated. The refraction direction T is expressed as the combination of the normal vector and a vector that is perpendicular to it. This perpendicular component is called n perp or n perpendicular. It's here. N perp is expressed from v plus n times cosine alpha because these vectors are parallel to each other. The only difference is that n perpendicular is assumed to be a unit vector. So to get n perpendicular, we take this vector and normalize it, which means that we divide with the length of this vector. The length of this vector is just sine alpha because here we have a right triangle where the hypotenuse is 1. T is the combination of n and n perp using the Snell's law and denoting the refraction angle by beta. T is nothing but n perp times sine beta and minus n, because it points into the opposite direction, minus n times cosine beta. Let us substitute this formula into the n perp expression. We can replace sine beta divided by sine alpha with the reciprocal of the index of refraction according to the Snell's law, here and also here, and we just group the terms that depend on normal vector n. We are getting close to the solution. Then cosine beta is replaced by sine beta using the fundamental relation of cosines and sines, and finally sine beta is expressed with the sine alpha, again using the Snell's law. And in the final step, sine alpha, or the square of sine alpha, is expressed by cosine alpha using the trick which was used here again. We can establish this final result, which is a formula taking the incident direction and the normal vector as inputs, and also the index of refraction, and returns a unit vector that specifies the refraction direction. This final formula for refraction direction involves a square root here, where the discriminator, which is in the square root, can also be negative if the refraction index n is less than 1. This relative refraction index is less than 1 if the ray arrives at the boundary from an optically denser medium. For example, when the ray is originally in water and meets the surface separating water from the air. Negative discriminator indicates that there is no refraction direction because the light gets fully reflected. This situation is called the total internal reflection, and the threshold angle when it first occurs is the Brewster angle. The picture here shows a swimmer, in fact he is Cseh László, an Olympic silver medalist, who is below the water surface while the camera is at the bottom of the pool. The water surface here acts as a perfect mirror, reflecting the back of the swimmer and also the bottom of the pool. Surfaces are usually not perfectly smooth, so they can reflect light not just in the ideal reflection direction, but practically in all possible directions. This can be interpreted with the following model. On microscopic scale, we can imagine that these rough surfaces are random collections of ideal mirrors called microfacets, and they reflect light according to their random orientation. As we see, not just a single microfacet in a pixel or on macroscopic scale, but a large collection of them, we perceive the average radiance reflected by this collection. So when we have just a single beam, because of the random orientations, this average can be non-zero in all possible directions. Photons may have just a single light surface interaction. On the other hand, photons may interact with the surface several times, and during that they tend to forget their original direction. And as a result, the reflection lobe is large in the vicinity of the ideal reflection direction, but non-zero in other directions. Instead of the probabilistic reasoning, which would be rather exciting, we use a simpler approach and handle these rough surfaces with a black box model, also called empirical model. It means that we describe the behavior of the surface based on everyday experience without any structural analysis. By experience, we say that rough surface reflects light into all directions, but more light in the vicinity of the ideal reflection direction. The reflected radiance of a surface depends on the irradiance or the and also on the likelihood of reflection. The irradiance is the incident radiance multiplied by a geometric factor that is just a cosine of the angle between the illumination direction and the surface normal. This geometric factor expresses that the illumination gets weaker if the light arrives from a non-perpendicular direction, since the light is distributed to a larger area than the cross-section of the beam. The likelihood of the reflection is called the bidirectional reflectance distribution function, or BRDF for short, and we usually denote it with FR. So by definition, the BRDF is the reflected radiance divided with the incident irradiance. In real life, BRDF functions are symmetric, which is often referred to as the Helmholtz reciprocity principle. In computer graphics, BRDF is just a formula for us, so we can work even with non-symmetric BRDFs as well, but we have to understand that these materials cannot exist in real life. Our first model is for very, very rough surfaces where all photons get reflected multiple times. Such materials include snow, sand, wool, chalk, clothes, and so on. And indeed, they have a matte look, and they look the same from all viewing directions. The reflected radiance, which equals to the irradiance multiplied by the BRDF, is independent of the viewing direction. The irradiance is obviously independent of the viewing direction, so as a result, the BRDF must also be independent of the viewing direction. According to Helmholtz reciprocity, if the BRDF is independent of the viewing direction, it must also be independent of the illumination direction. So, as a result, the BRDF for diffuse surfaces is direction independent or constant. Well, it may depend on the point and also on the wavelengths, but not on the illumination or viewing directions. Thinking of the microfacet model, diffuse surfaces correspond to very rough surfaces when photons collide multiple times. The Fresnel function describes the change of the color in a single reflection, and for non-metals, the Fresnel function is quite close to white, so there is not too big difference for different wavelengths. But even if a single direction changes the spectrum just a little, multiple reflections amplify this effect, so the final refracted light will have a strongly modified spectrum. Diffuse reflection is therefore responsible for the so-called own color of the surface. So this diffuse reflection parameter is heavily dependent on the wavelengths. The reflected radiance is the incident radiance times the BRDF, which is a constant KD for diffuse reflection, and the geometric term, which is the cosine of the angle between the surface normal and the illumination direction. So this is the formula to compute the reflected radiance for diffuse surfaces. It's also called Lambert's cosine law. This cosine can be computed with a simple dot product if the normal vector and the illumination direction are unit vectors. I have to say a few words about this plus sign in the superscript as well. Well, when this dot product results in a negative number, it means that the surface is illuminated from the back, so from that side where the object is whose surface we are talking of. So the object itself occludes the light source from this surface point. So here, in this situation, instead of negative numbers, we replace the result by 0. So that is emphasized by this plus superscript here. Shiny, glossy or specular surfaces also reflect light in all possible directions, but more around the ideal reflection direction. As a result, we can see a blurred reflection of the light source because they reflect more light close to the reflection direction. We model such surfaces by two terms. The first term represents the uniform reflection lobe in all directions and described by the diffuse reflection model. Then we add a reflection lobe which is non-zero only around the ideal reflection direction. According to the microfacet model, diffuse reflection is caused by multiple light microfacet interaction, while specular reflection is the result of a single light and microfacet interaction. In order to model the specular lobe, we need a function that is maximum at the reflection direction and decreases in a controllable way if the viewing direction gets farther from the ideal reflection direction. Fong and Blin proposed the shininess power of cosine function to describe that controllable decrease. In this formula, delta is the angle between the surface normal and the halfway direction or halfway vector h that can be computed as the in-between vector of viewing direction v and illumination direction L. So if L and V are unit vectors, h can be computed by adding them up, and as we want to compute the cosine as a simple dot product, we have to normalize the result. The shininess exponent defines how shiny the surface is. Considering the microfacet model, this factor is proportional to the probability density that a random microfacet reflects the given light direction L exactly into the given view direction V. That is, the normal vector of the reflecting microfacet is just h, which is in between V and L according to the geometric law of reflection. Diffuse reflection simulates multiple light surface interaction, and as a result, diffuse reflection is usually colored. Specular reflection is the model of single light surface interaction, and it is proportional to the Fresnel function. For metals, the Fresnel function is colored, but for non-metals, the wavelength dependence of the Fresnel function is very moderate, in fact negligible. So for non-metals, the specular reflection is set to be white. So if the light source is white, the glossy reflection on the surface will also be white. Adding up the diffuse and the glossy reflection, we have the impression of nice shiny surfaces. To simulate a rough material, we need a shade function that computes the reflected radiance for incident radiance in red, incident direction light there, view direction view there, and surface normal normal. Since the reflected and incident radiances are spectra, we use Vec3 type to represent them, which can be different on the wavelengths of red, green and blue. This function first computes the geometric factor cosine theta. If this geometric factor is negative, then the back of the surface is illuminated, so the object itself occludes the light source, so the reflected radiance is 0. Then, if this is not the case, the diffuse reflectance is computed. Finally, the diffuse reflectance is increased by the specular reflectance, which is just the direct implementation of the Fong-Braun formula. Real light sources are determined by their emission radiance, usually denoted by LD, and it can depend on the point, on the direction, and on the wavelengths as well. So when the reflected radiance is computed at a particular point, all possible illumination directions should be considered and their contribution should be added. If there are infinitely many such points in any continuous domain, addition means integration. Integration is difficult, so we prefer so-called abstract light sources that save integration for us. Abstract light sources have the property that they can illuminate the surface only in a single direction, so we don't have to integrate. The first model of abstract light sources is the model of directional sources, where the radiance is constant everywhere, so is the illumination direction. In other words, illumination rays are parallel. Here, on planet Earth, Sun is a good example for a directional light source. The second model is for point light sources, where the illumination direction of a particular point is just the difference of the position vector of this point and the position vector of the point light source. And the radiance decreases with the square of the distance in this case. Small light sources are again good examples for positional lights. Rendering requires the determination of the surface that is visible through a pixel, then the computation of the radiance in the direction of the eye. There are different trade-offs between accuracy and efficiency in this computation. In the so-called local illumination setting, when the radiance of a surface is calculated, we consider only the illumination or the direct contribution of the light sources and ignore all indirect illumination completely. In recursive ray tracing, indirect illumination is computed only for smooth surfaces and in the ideal reflection and refraction directions. In global illumination model, indirect illumination is taken into account for rough surfaces as well. So for a single point, we consider infinitely many potential illumination directions. I have to emphasize that in engineering applications, for example as lighting design, we need global illumination solutions, since only these provide predictable results that are similar to the real-world observations. However, in games or in real-time systems, local illumination or ray tracing will also be acceptable because we don't have to compare the result to some ground truth.